What we have here is 3 points in technically 3D space, in reality obviously on a flat surface. What we're asked to do is determine the equation of the plane that contains those 3 points. So if I was to draw some kind of representation of a 2D plane in 3D space, look a little bit like this. And I would then join up my points A to C, C to B. I don't need to join A to B because what I want to do is I want to try and find two vectors, A and vector B. Okay, so obviously vector A in this scenario is from A to C, which is equal to C minus A. Okay, and then we've got a second vector B, which is from C to B or B to C, and that's going to be equal to, by definition, C minus B. Okay, so we've got two vectors. Why do we need those two vectors? Well, what we're trying to establish is the normal of both of those. So effectively we have a vector of A and we want it to be 90 degrees, n be 90 degrees to A, and we also want n to be 90 degrees to B, i.e. 90 degrees to both of them. And that normal vector will give us the tools to actually work out the equation of the plane. I'm going to call that plane pi, okay, and that becomes equal to ax plus by plus cz equals some constant, okay. So basically A, B and C will determine the how the plane sits in 3D space, and the value of k will move it up and down. And in actual fact, our normal vector by definition is the three coefficients A, B and C. So if we can find our normal vector, then we can work out our equation of our plane pi. So how do we do that? Well, this is where the cross product comes in. A cross B is actually going to be equal to a vector which is perpendicular to both, which is our normal vector. Okay, so we're going to find out what A cross B is, but before we do that, of course, we need to work out what A is. So A is going to be, so C subtract A, 1 subtract 3, so that's -2. 2 subtract 1, and then -3 subtract 2, -5. So there's our vector A, and then our vector B, similarly, is going to be equal to C minus B. So 1 subtract 1, that's 0. 2 subtract 0, that's 2. -3 subtract -2, so we're adding 2, -1. So those are the two vectors A and B we need. All we now need to do is find the cross product. So I'm going to do that next. So there's quite an elegant way of actually working out the cross product, even though the cross product is actually given as a formula in the Further Maths formula book. We can actually do it by determining or figuring out the determinant of this vector with I, j and k being the first row, and the components A1, A2 and A3 being the components of A, and similarly B1, B2 and B3 being the components of B. So if I was to do that using our standard means to find determinants, I would obviously block off my row and column, and I'd end up with the determinant of so our minor matrix A2, A3, B2, B3, and then multiply that by I, and then minus, because of course the matrix of signs would flip the sign of my second one. So again, I would cross through here, and I'd end up finding the determinant of A1, A3, B1, B3, multiplied by J, put little hats on, and then finally, which I want to do here, plus my final column blacked out, so A1, so determinant of A1, A2, B1, B2, and that's multiplied by K. Okay, so what that will do is will give us our matrix, our vector, which is going to be the cross product of A and B, which is going to be the normal, which is what we're after. So A2B3 minus A3B2, and that's multiplied by I, plus or minus here rather, and then we've got A1B3 subtract A3B1. Notice, of course, B1, and that's J, and notice, of course, A1 and B3 flips with A3 and B1, and then finally plus brackets, and we'll just about squeeze this in. A1, B2, subtract again A2, B1, and that is multiplied by K. So that's going to give us our normal vector. So what we've got to do is plug in our values accordingly, okay, from our two matrices up here. So in this case, we're going to have A2, which is 1 times B3 times -1, subtract A3, which is -5 times B2, which is, so that's subtract -10, okay, and then we're going to say also it's going to be multiplied by I, and then we're going to subtract A1 B3, so A1 -2 times, so that's going to be +2, subtract A3 B1, so A3 is going to be -5 times 0, conveniently, so that's J, and then plus finally A1 B2, so -2 times 2, which is -4, subtract A2 B1, so it's 1 times 0, subtract 0, and that's going to be K. Okay, so tidying that up, we end up with -1 subtract -10, so that's going to be 9, so adding 10 to -1, 9i, and then 2 subtract 0, it's going to be subtract 2j, and then finally -4 subtract 0 is going to be -4k. Okay, so that cross product should give us the normal vector. So the final thing to do is plug my normal vector into my equation for the plane. So I know my normal vector tend to write it in column form, so it'd be 9, -2, -4. And then we can replace these coefficients of x, y, and z. So we end up with 9x minus 2y minus 4z equals k. So k is going to give us our unique plane in that kind of stack of planes, if you wish. And we can just choose one of the 3 points. Logically, I'm going to probably choose B because it's got a 0 in it. So I know that if I set coordinates 1, 0, -2 into my x, y, and z respectively, I end up with 9 minus 0, -4 times -2, so that's +8 equals k. So therefore, k is equal to 17. So finally, my plane pi is going to be equal to ax. So we got 9x minus 2y minus 4z equals 17. Okay, so there's our plane. I'm just going to show you visually what that looks like.
Okay, as you can see, we have the XY plane. That's the grey area with the red and green axes, and the blue axis, which is the vertical z-axis running upwards. And we have our 3 points: A, 3, 1, 2, B, 1, 0, -2, and C, 1, 2, -3, which makes our triangle in 3D space. So rotate that so you can kind of see what the triangle looks like. It actually cuts the XY plane. And obviously what we just calculated was the plane that connects or contains those 3 points and contains that triangle. So we're going to overlay that plane and see if we were successful. So this is a reminder, -9x plus 2y plus 4z equals -17. So we're just going to put that plane on. So you can see the blue plane now appear. It's not obvious until I rotate it that actually the triangle is contained within that plane, A, B, and C. And then you can rotate it again, and you can see, once again, the triangle is completely contained. So there is our solution in visual format. Okay, thank you very much.